This screencast follows on a discussion earlier about the debate concerning the nature of light. You have Isaac Newton on one hand, Christian Huygens on the other hand. Isaac Newton thought that light was made out of particles, which he called corpuscles, and Huygens thought that light was made out of waves. As a result of that discussion, where I explained the different properties of light that needed to be illustrated by the appropriate model, we talked about the fact that light would travel in a straight line, rectilinear propagation. Light could be reflected, light could be refracted, and those were the properties of light that were known at the time of Newton and Huygens. We mentioned the fact that Newton's model predicted that light would speed up entering a denser medium, and Huygens' model predicted that light would slow down entering a denser medium. Later, when they figured out what the speed of light was, as well as when they discovered some other properties of light, such as diffraction and interference, Christian Huygens' model stood the test, and his model could explain those properties, and Newton's model could not. However, towards the end, there was the photoelectric effect that was discovered, something we'll talk about in a later chapter. And Newton's model could explain that, Huygens' model could not. That is why we say that light has this dual nature. It is a particle in some experiments. It acts like a wave in other experiments. Of course, light is light. It is unique. It is not technically one or the other. It's so profound, we actually need two models in order to explain it, or at least to understand it. And then I suggested the fact that if light could have a dual nature, particles called photons, which have wave-like characteristics, particles of energy, maybe other particles could also have a dual nature, such as electrons, and for that matter, we could go as big as baseballs and cars and so forth. And the answer is yes, they do. So I'm not going to go over this debate between Huygens and Newton. Once they knew about diffraction, once they knew about interference, once they were able to calculate the speed of light, everyone went towards light being made out of waves. But then when the photoelectric effect was discovered, then we concluded that light must have a dual nature. Incidentally, it's rather interesting to note that before they realized that space is empty, or at least one particle per cubic centimeter empty, which is about as close to a vacuum as you can get, and we've never achieved a vacuum as good as outer space, as far as I know, on this planet. They used to think that light was made out of this material called ether. So if light was traveling with the ether, it would be traveling faster than if light was traveling against the ether. And when we get to Einstein's theories of special relativity, we'll see that he abandoned the idea of ether and made some remarkable and intuitive discoveries. We'll talk about photoelectric effect in a later chapter. Please remember Shaw's definition of light. Packets of energy called photons, which actually have wave-like characteristics. So it's both a particle and a wave. And those particles have a certain amount of energy, and that energy is proportional to the frequency of the wave. And so the proportionality constant becomes Planck's constant, and you can see that it is quite small. In a future chapter, we might mention things like Planck time and Planck length as being the smallest interval of time and the smallest length that can possibly be measured. So, one more time. Depending on the experiment, light behaves like a wave or like a particle. So if I ask you, is light a wave or a particle? You could correctly answer by neither, and you could correctly answer by both. I think the best answer is that light is light. It's something absolutely unique. And it technically isn't a particle or a wave, nor is it both at the same time. But we just don't have an adequate model that explains how profound and amazing of a creation it happens to be. Well, two of the properties that both models were able to explain were reflection and refraction. Reflection, of course, is reflecting off a surface, bouncing off a surface. Refraction is bending as it goes through from one medium to another medium. And we use a lot of geometry when we talk about rays, a ray or beam of light. And this geometry, for example, ends up being the angle of incidence equals the angle of reflection when we talk about either a wave or a particle striking a barrier. But we'll get to that in a minute. Just for the record, most of the time we're going to be talking about a light bouncing off a very, very smooth surface or specular reflection. Of course, realistically, no surface is perfectly smooth, but when you have irregularly planed surfaces, such as this down here, you're going to get diffuse reflection, and you're going to get arrows bouncing off all different directions, rather than predictably at the same time in the same direction. And this is what it would look like in a dark room using a beam of light shining on a surface. Please note that if this is the barrier right here that the light is bouncing off, and let's say it's coming this way and bouncing off that way, we always like to make a normal line. That's my normal line, which is perpendicular to the surface, and that this angle of incidence, or incoming light, equals the angle of reflection, or the reflected light. And you might see that if it's a misty, moisty day, and there's a lot of water vapor in the air, as opposed to on this side where the water is just on the surface. There's more reflection in specular reflection in figure A, and there's more diffuse reflection in figure B. Another way to say that the angle of incidence equals the angle of reflection, and sometimes we can use that for our letter R, is to say it like this. The I is the incoming or incident beam of light, and then the R is the reflected. And they're not using an R here. But that's the angle of reflection. They mention the fact that some of the old-fashioned pictures, if the source of light that's being used to illuminate the subject's face is very, very close to the lens of the camera itself, the light will bounce off the back of the retina and will appear red due to all the capillaries in the back of the eye. And you get this thing called retroreflection, which is really not all that important for our purposes in this chapter. If we look at this problem, we can make more complicated and interesting problems by saying, what if our light is bouncing off of multiple surfaces? So here's my incoming light. Notice again, my normal line is perpendicular to the surface, right angle. And we always measure our angles from the normal line. We do not measure our angles from the surface. Don't do that. So I'm going to erase that. Don't measure it from there. Always measure it from the perpendicular. And so if it comes in at a 65-degree angle, it's going to go out by a 65-degree angle. Now, if it strikes this other surface here, we can calculate, if this is a 120-degree angle, we can calculate what this angle must be. If we know that this is 65, this is going to be 90 minus 65. And so this angle right up here is going to be 360, the number of degrees in a triangle. Let's erase that. Yeah, not the number of degrees. And we can calculate this angle and this angle, subtract it from the total angle to find this angle, which then helps us find this angle, because they have to add up to 90 degrees, which gives us that angle. Now, as far as refraction is concerned, the amount that light is fracted or bent when it enters from one medium into another depends upon what those substances are. Notice that the plural for medium is singular, media is plural. It's from the Latin. And so if we have two media and light is coming through one medium and being bent at the interface where it enters another medium, we can see that the ratio of the sine of the refracted angle, theta 2, divided by the sine of the incoming or incident angle, theta 1, has the same ratio as the slower velocity in the denser medium compared to the not so dense medium, and this equals a constant for those two media. We should also say that this path is reversible. And so if we look at the diagram down here, if this is my normal line, perpendicular to the point in which ray A strikes my glass surface, here's my angle of incidence, and some of that light at the point of impact will be reflected. And those two angles will equal each other. But some of the light will pass through. And you'll notice that this angle, theta 2, is smaller than theta 1. Theta 1 is bigger than theta 2. In other words, we say that ray A is being bent towards the normal. If this is the normal, it's closer to the normal here than it was up there. It's being bent towards the normal. That's the language. And that is always true when light enters a denser medium. But we can also say, and I'm going to erase this, we could go the other way. If a light is going through a denser medium, and let me just make sure I just write here, it's going to be bent away from the normal when it goes into a less dense medium. So it is reversible. And over here, you can see a picture of this beam of light being bent towards the normal, reflecting off the surface, and then over here, this angle and the bigger angle being bent away from the normal. So the law of refraction, there we go. The law of refraction, and there are different aspects of this, says that the speed of light in a vacuum is always greater than the speed of light in any other medium. Light travels the fastest through space. Therefore, the value of n is always going to be greater than 1. If it is staying in the vacuum, of course, it would equal 1. It's always greater than 1. Now, we might say, well, why does it slow down when it enters a medium of greater density? And down here, you can see that there is a time lag, because every photon of light, every particle of energy gets absorbed by some atom that makes up the composition of the denser medium, and then that photon of energy is spit out, and that takes a moment of time to do that. And that slows down the beam of light when it's going through a denser medium. Now here's a chart of some of those indices of refraction. The plural of index is INDICES. This is plural. Index is singular. And you can see by far and away, diamond is the biggest. It's why diamonds sparkle so much. Though if you have a cheap substitute, you might use something that's a distant second, a zirconium diamond. You also notice that liquids have, some liquids have densities, or I should say indices of refraction, very similar to glass. For example, if you had some benzene and you had some crown glass, they both have very similar indices of refraction. Notice that you have to go to the hundredths place before you begin to see some difference. Now, in forensic science and solving crimes, there are many, many, many different kinds of glass. And glass is a frequent clue or artifact at a scene of a crime. There are glass goblets and glass jars and glass windows, glass mirrors, glass from eyeglasses. There's also glass headlights on a car. The glass windshield is different from the glass on the side windows, which would be different from the glass on the rear view mirror. There are many, many different kinds of glass. And so if you have a spectrometer, if you have a device for measuring the index of refraction that's capable of going to the hundredths or thousandths place, you can identify which kind of glass it is: crown glass, flint glass, Pyrex glass, some other kind of glass. Many different kinds. Notice that the speed of light in air is so close to the speed of light in space that the index of refraction, at least to 4 significant digits, would be 1.000. Carbon dioxide is a little bit denser than air. Now, this is a very important point. As light travels from one medium to another, its frequency doesn't change, which means it stays the same color. If the frequency did change, the frequencies could sort of pile up on top of each other. But if the frequency doesn't change, and we look at the equation that says that speed equals wavelength times frequency, if the frequency is constant, that means if the wavelength goes up, the speed has to be reduced. By the same token, if the wavelength got smaller, then the speed has to get greater, and vice versa. That's assuming the frequency remains constant when it goes from one medium into another, and indeed it does. We can say then that the index of refraction is inversely proportional to the wave speed. The higher the index of refraction, think of going from glass to diamond, for example, the more the speed of light will be reduced. It'll slow down. Another way that we can find the index of refraction besides comparing speeds is therefore comparing wavelengths. Obviously, we can't compare frequencies because that doesn't change. Then we get this equation right here, perhaps the most famous equation in refraction, called Snell's law. And that is if you multiply the index of refraction of medium number 1 and you measure the incoming angle with respect to the normal line, that will equal the index of refraction of medium number 2 and the sine of the angle for medium number 2. So imagine you're entering a denser medium. That means that the index of refraction as you enter a denser medium is going to be greater. But remember we said that the light is bent towards the normal, so your angle is going to be smaller. That's Snell's law of refraction. And I would encourage you to do these little quizzes and look up the answers in the back of the book to test your understanding. And most of these math problems, I think, are quite simple, but it's good to look at some of the remarks. The light ray bends towards the normal, third time I've mentioned that, I think, when it enters a medium or a material that has a higher index of refraction. The other interesting thing is when it exits that material, it ends up coming out parallel. So if we look down here, this beam of light right there, when it comes out here, is parallel. They're parallel to each other. It's bent towards the normal, and then it's bent back away from the normal, and now the beam of light is headed in exactly the same direction. It's just offset a little bit. In this problem right here, the text says it's interesting to note that the speed of light in a vacuum is the upper limit. And to 3 significant digits, we use 3.00 times 10 to the 8th meters per second, or 10 to the 5th kilometers per second, or 186,000 miles per second. Now, maybe you recall from grade school, maybe not, playing with a piece of glass called a prism. A prism would be a solid piece of glass that might look something like that. And as the light goes through the prism, the light gets dispersed. And oftentimes you see a rainbow of color as a result of the light going through that glass prism. And that is because every one of the wavelengths is bent slightly different from every other of the wavelengths that make up white light. White light contains all the wavelengths of color, and those wavelengths of color down here are red, orange, yellow, green, blue, indigo, violet, though I never could see much difference between indigo and violet, but it helps to make a guy's name. But each one of those wavelengths will be bent differently than the others. And here's how I remember that. I remember that red, let's start over here. Blue is bent the biggest or most. B, B, B. Blue is bent the biggest. And trying to come up with another one, we could say that red, R, is refracted, R, the least. And for those of you that don't get the joke, I'm just using the word least, but I'm beginning with an R. Red is refracted the least, blue is bent the biggest. And that's how you can remember what happens when white light enters a prism. Now, the amount that it's bent away from its original direction is called the angle of deviation. We can use a prism spectrometer to spread the light out into its corresponding spectral lines or wavelengths down here. And here, I hope you remember a lab that you might have done in honors chemistry, where you put different pieces of wood that were soaking in different salts into the flame of a Bunsen burner. And when you looked at the flame, you got different colors of flame because every metal salt produced its own unique color. And if you were to look at that color through a spectroscope, it would spread the color out into its spectral lines. Another way that you did that was you took some glass tubes that had gases in the tube like helium or argon or neon or carbon dioxide or hydrogen. And when you zapped it with electricity and looked at the unique color of light through a spectroscope, you again could see unique spectral lines. And these spectral lines form the fingerprint of that particular element. In the hallway past my door as you enter my room, right there on your left, heading towards the desks, you'll see the spectral lines of a whole bunch of different elements. They are a fingerprint. So if we come over here, here is my blue is bent the most, whereas my red is bent the least. And there are all kinds of different spectrometers that can spread the light out so you can see the individual spectral lines that make up the unique color. And this is a powerful tool in astronomy. It's one of the tools that helped us to realize that the universe is not just expanding, but accelerating. We can use it to identify molecules or metals. Astronomers can use it to identify the elements that might be present in distant stars by allowing the light coming from the star to go through their telescope into a spectrometer. Or in forensic science, or any other kind of diagnostic science, you could identify an unknown material or mineral or metal by its unique combination of spectral lines. I'm going to stop there, and we will continue later.